The gravity of the time is such that every new avenue of peace, no matter how dimly discernible, should be explored. Never before in history has so much hope for so many people been gathered together in a single organization. You will provide a great share of the wisdom, of the courage, and the faith which can bring to this world lasting peace for all nations and happiness and well-being for all men.
Welcome back to another episode of Titans of Nuclear. Today I am in person at the Georgia Institute of Technology sitting down with Dr. Dan Kotlyar, and he is a newish associate professor, I've heard, and he's working in the Computational Reactor Engineering Laboratory, also known as CORE. Dan, welcome.
Hi.
Hi. It's so nice to have you on. I'm excited to chat with you today. So before we delve into your current work, let's just go ahead and talk a little bit about your background. Where are you from?
Oh, that's a tough question, I guess. So I'm from Israel originally. Well, born in the Soviet Union, immigrated to Israel, did my PhD there, and then had a journey to being a postdoc in University of Cambridge in England, and then I was offered this position in Georgia Tech, and now I'm here.
That's awesome. And so did you do your schooling at all of those places, or is that kind of where you worked in other professor jobs?
Well, I did my undergraduate, master's, and PhD in slightly different topics, but most of them were in nuclear engineering. Mm-hmm. My undergraduate was partially with electrical engineering as well, mm-hmm. but I've decided that nuclear was much more fun, I would say, much more exciting. And so that's where I've done my schooling. I actually became a part-time lecturer even during my PhD. I've found that to be extremely interesting. So I developed a passion of teaching. So I've been doing this in Ben Gurion University. That's the university in Beersheba in the south of Israel. And then I applied for multiple places, and one of the places that I really wanted to live was in Europe. Cambridge sound like a great place to be in at that time, and so I went and did my postdoc. So it's no schooling, just research work, and I was mentoring students in Cambridge University, but also doing my research there. And then since I came here, what I do is, as an assistant professor and recently as an associate professor, is to teach students. Mainly I teach reactor physics courses and reactor engineering courses. And recently I started doing an experimental lab, which is even better. All that theoretical stuff is a bit boring sometimes. And I guess my lab is doing the research with me on topics associated to reactor physics and reactor engineering.
So let's take it back a bit. What led you to the decision to pursue nuclear?
It's an interesting question. I'm not sure I have an easy answer. You know what?
That's okay.
When I was 18 years old, we go to the army first, and then we graduate with the army, and we go to the university. I honestly didn't know what I want to do. I knew I want to become an engineer. I was sort of good in math and physics in my high school, and I've decided to pursue a path of an engineering path. But what type of engineering, whether this is mechanical or electrical, I didn't really know. I think that's what pushed me towards this. It was not dual, but it was a nuclear engineering with a major in electrical engineering, which is a bit odd, I think, right now when I'm saying this, is most of my courses were actually electrical engineering. And I started doing research in my junior year, and that's what I actually promote here in Georgia Tech as well. I try to encourage our undergraduate students to do research with any faculty in Georgia Tech. So I started doing my research in nuclear engineering. It was energy-related fuel cycle analysis of typical light water reactors commonly used in our industry. And I fell in love in the nuclear for energy, I would say. And so I've sort of abandoned the electrical field, although some of the subject helped me later on as a professor even. Yeah.
Awesome. And so what are you specifically teaching here at Georgia Tech now?
Well, I teach reactor physics, reactor theory, which are, a continuation of courses. It's like fundamental of reactor physics. Students are supposed to understand the basic mathematical models to link between the theory that sort of describes how a reactor would behave, how the reactor would look like, and why we design the systems in such a way. And then we dive into more practical applications, and they sort of, the mathematical level would increase in depth, but also their understanding of how the systems actually operate. Either this is in a sort of like a nominal operation or off nominal, for instance, accident scenarios or something along those lines. It doesn't have to be an accident; it could be some type of off nominal perturbation, I would say, and the students would gain that understanding during my classes. Another course that I've taught for 2 years now is the graduate reactor engineering course, and this is sort of like a broad but in-depth overview of the specifics of light water reactor systems. Mm-hmm. Those are, most of our reactors are pressurized water reactors or boiling water reactors, so we typically focus on those. We do have advanced systems as well that we teach, but if you sort of understand how the light water reactor operates, it gives you enough tools to understand other systems as well. And so they dive into systems of how would you do fuel management, for instance, in the system. Why would you do it in such a way from an efficiency point of view? But they also understand things like how would the fluid flow, in this case, water flow inside the light water reactor. And they would try to understand the thermodynamic efficiency and why we design systems in such a way, and that is taught in the reactor engineering course. And recently I was asked to teach an experimental reactor physics lab, which I found to be even more entertaining for myself as a professor, maybe not necessarily for the students as much. They have to do a lot of work there. But it's sort of going to the lab and trying to link the theoretical model that we teach during the reactor physics classes to actual applications in the lab itself.
Mm-hmm. And so let's narrow in and focus on that a little bit. Would you say that's kind of your favorite area to teach?
The experimental reactor physics?
Yeah.
Recently it became my favorite area, but because my background is reactor physics really, mm-hmm. and eventually all my students would have to apply that knowledge during the research. I would say reactor physics, the core reactor physics, the hardcore reactor physics, where they need to understand different computational methods, because those methods would allow them to sort of design a better system, I would say. Mm-hmm. With less assumptions maybe, and better safety margins, for instance. So that's why reactor physics is still my favorite course.
Mm-hmm. That's awesome. And I also hear that you're very interested in space. So let's talk a little bit about nuclear thermal propulsion and rockets and all of that good stuff.
Yeah, we can. Is there any specific that you want to talk about? Because I can start now, and probably that would be our last discussion point here.
Let's start delving into that a little bit, and just go ahead and start at the beginning, or what interests you the most. It's probably tough to kind of zero in on that,
okay,
because there's so much to talk about.
So let me just comment on my background again, and provide a background story before I start with specifically the space propulsion system.
Great.
So my background in general is either designing advanced systems, fission systems. I'm focused on fission systems mainly, and those would be different generation 4 reactors, for instance, or even our own in-house developed systems that we are trying to develop here. They can either provide a benefit to an existing light water reactor system, or even we can focus on a light water reactor system and develop a better fuel cycle that may improve the fuel utilization, for instance. So meaning that that the cost of your fuel would be cheaper essentially, or my apologies, the cost of the fuel cycle would be essentially cheaper. And that is something that we do with companies that we work with. So for instance, my group works with Framatome to develop and push industry interests in developing a better fuel cycle. And I guess up till 4.5 years ago, I've honestly never heard of nuclear thermal propulsion before. And so, as I said, I encourage my students to pursue their research goals and get some research experience during their junior and senior year as undergraduate students. And if they like it, they can either pursue through their masters or PhDs, or they develop just the worst scenario, they simply do have some research experience and they go to the industry or to the national labs with some tools, which, I mean, again, I guess it's a win-win situation for everybody. And I guess 5 years ago, a year and a half after I started in Georgia Tech, a group of undergraduate students after one of my reactor physics classes came to me and said, well, have you heard about the nuclear thermal propulsion concept, and would you be willing to mentor that project? And I said, well, I know nothing about that, but yeah, most definitely, let's do this. And so they came up with all the literature review. They taught me most of the stuff that I know today, I guess. And it, of course, it evolved since then. But I've discovered a very interesting reactor concept. But even more than that, it's not really a reactor concept, because in reality, there were 20 systems, nuclear thermal propulsion systems, that were built and tested, ground tested. And this is sort of known as, and this now brings me to that topic. This is the nuclear thermal propulsion had a golden years from 1955 till 1973 under what is known to be the Rover program. Okay, the Rover program, I believe, was initiated in Los Alamos, and it was sponsored by, by the U.S. Air Force and the Nuclear Atomic Commission. And the main idea was to develop a program, or advanced nuclear thermal propulsion program for ballistic missiles. But soon they've realized that they can use the same technology to send crewed mission to Mars. Okay. Okay. So that's sort of like the background here. And what happened after that is, I guess the Rover program had multiple sub-programs. One of those was known as the NERVA program. So a lot of the times, Rover / NERVA. NERVA is, the nuclear rocket vehicle application. I forgot the E.
No worries.
That's fine. So the objective of the Rover / NERVA program was to demonstrate the feasibility of a nuclear thermal propulsion engine. Oh, the engine. E stands for the engine.
Perfect.
Silly me.
No.
Silly me. Okay, so they had multiple sub-programs, and they have so many. As I said, they built 20 systems. They ground tested those systems as well, and I will just mention a couple of those, because those are sort of the milestones for today's programs that we have in the United States, mainly in the United States. Okay, so some of those programs were the first one was, they were all exotic fruits. I'm not entirely sure why. So the first was kiwi, the second one was phobos, and the third one that I will mention would be the peewee. And again, as I said, most of today's systems sort of borrow same characteristics of those previous ones. So the Kiwi one, for instance, was the first series of reactors, nuclear thermal propulsion reactors. Again, nothing was tested in space. Everything was ground tested. The Kiwi started with developing the first set of reactors. Kiwi A, I believe, was tested in 1959. Okay, a while back.
Yeah.
And it operated only for 5 minutes, and it was operated for at a power level of 70 megawatts. So I'll just give you a context. A typical light water reactor, for instance, operates at anywhere between 3,000 and 4,000 megawatts thermal. This system operated at 70 megawatts. This is a much smaller system, only for 5 minutes, although a light water reactor, for instance, would operate for years under the same fuel. Okay, so here we are looking almost like for pulse type of operation, because we don't need to operate that system for a long period of time.
Right,
so
okay.
it operated for 5 minutes, and they did like a post-analysis of the fuel, and they've discovered that the fuel was correct, that the fuel reacted with the hot hydrogen. I'll explain why we use the hot hydrogen a bit, and that some of the fuel was lost. It moved through the fuel elements and was lost. Obviously, that's something that you wouldn't want to have. And so, as I said, there was this first series. The second series, FUBUS, was meant to improve some of those lessons. And so they use coated particles, for instance. And again, those are very high temperature applications. The idea, you know what, I'm probably jumping from subject to subject. I'll finish with this and I'll give you some context of why we need to have high temperature as well. So FUBUS, for instance, operated for 10 minutes now, and it meant to operate it at much higher power, because the idea was to demonstrate the feasibility of a nuclear thermal propulsion system. So instead of the 70 megawatts, it operated at a 1,000 megawatts, much higher power rate, and at that time it set a record of having a propellant temperature reaching slightly less than 2,300 kelvins. That's very elevated temperature, and the fuel peak temperature was, I believe, was slightly less than or around 2,400 Kelvin, which again, is enormous in my opinion. And the third series, which was an improvement to both, was, I believe, tested with the PW series of systems, and a lot of today's systems actually are based on that series. PW was the smaller scale of FUBUS. It was designed as a 500 megawatts, and it set a record of 2,550 kelvins in propellant temperature and 2,750 kelvins in terms of the fuel peak temperature, which is again extremely high. I mean, we don't typically operate reactors or our light water reactors under such high operational conditions. Okay, so maybe why do we need to operate these systems? I guess I would have to explain a couple of terms here. So I guess the metrics to define a propulsion system would be thrust, what we know thrust, and specific impulse.
Okay.
So thrust is we essentially have a certain propellant. We want to accelerate that propellant and then expel that propellant from a nozzle. Okay, that's what creates the thrust. Okay, and with nuclear thermal propulsion, you create the thrust by heating a light propellant. In our case, that would be a hydrogen propellant, the lightest you can go. And it turns out that the lighter propellants have a much better efficiency in utilizing that propellant. So thrust is one. The second metric would be the specific impulse, but I'll first of all explain what is an impulse. Impulse is simply you take the thrust and you sort of integrate this over time. So it's like the total thrust. The total thrust from the ignition of the engine until through its operation. Okay, that would be the impulse. The specific impulse is when you take this total thrust, the impulse, and you divide by the amount of propellant needed. And this metric provides you how efficiently you are utilizing your propellant. Okay, and it turns out that the specific impulse behaves it has two main contributors to how the specific impulse would behave: the molecular mass of the propellant itself, and the temperature, the exit temperature, what we call the chamber temperature of the propellant when it exits the reactor. Okay, so the higher the exit temperature is, the better is the fuel, the better is the specific, or the higher is the specific impulse. So the better is the utilization of the propellant, and the lower the molecular mass, again, a better propellant utilization. So in principle, just to summarize, what you really want to do is you want to use light propellant, such as hydrogen, and to heat it to extremely high temperatures. Okay, and we want to heat the propellant to a temperature of around 2700 Kelvin.
Wow.
So, right, it's very high.
Yes, yeah.
Which implies that most of your structural materials would sort of exhibit even a higher temperature, which pose a design challenge, I would say. And that part of what my group does is developing computational methods to analyze such systems. Because nuclear thermal propulsion is a unique reactor, and sometimes for a unique system, you need a set of specific tools to be able to model those, and that's exactly what my lab is trying to do. We actually work with BWXT technology, and I can tell you more about that later on. So this is again the background of why basically we want to get the high temperature. And if I compare the nuclear thermal propulsion to other means of I guess technologies that exist, so you have the traditional chemical rockets that rely on combustion, but it turns out that nuclear thermal propulsion can provide comparable thrust levels. However, that specific impulse, that efficiency metric, could be doubled, which means that you can halve your traveling time to Mars. That's why nuclear thermal propulsion is is looked, at least now, as a promising technology, because the distance from Earth to Mars is around, well, it ranges between 50 and 400 million kilometers. It depends on the cyclic period, which changes every 26 months, I believe. But the idea is you have a large distance to cover, and so it poses a challenge and a specific dose for the crew. Okay, so if you now want to send a crewed mission, ideally you would want to minimize their exposure. And so nuclear thermal propulsion, as I said, can provide the same thrust levels as chemical, but get you to Mars and back much quicker. Okay, I guess that's just some background.
Yeah, no, that's incredible. And you mentioned the design challenge of having those really high temperatures. Are there some current approaches to solving that challenge, or is that still kind of an unknown area?
Oh yeah. So let me see. So first of all, there are multiple players that are looking on advancing this technology. As I said, this technology was developed by the Rover program. It was a slightly different fuel, but they did look on different fuel forms. So they looked on ceramic fuels, and recently the industry was looking into using ceramic metallic material, which allows you to reach those high temperatures. This is typically associated with a couple of different considerations. One would be the properties of the materials. I don't know how deep I should go there, but you want to have, first of all, a nuclear thermal propulsion system is not on. It's really different from a light water reactors. It's sort of, you need to satisfy different objectives. In the light water reactor, you want to provide a constant power for, a year and a half between reloads, for instance, of the fuel. You don't operate. Ideally, you would want to increase the power because you can basically improve the the fuel cycle costs, but not to make it too complicated to understand. The idea is that you work way below this, how would I explain? Give me 1 second. I'll try to rephrase myself here.
No problem.
So the idea is that you want to load the fuel, and the fuel provides you the energy. So you don't want the fuel to be depleted too quickly, because you would have to reload the fuel more frequently. And you want to operate for, let's say, 1.5 years or maybe 24 months, for 2 years.
Right.
Here, the operation is slightly different. You have different missions, but those missions typically have different maneuvers where the nuclear thermal propulsion would sort of satisfy. Those, in principle, you would have, for the outbound journey, you would have 2 trans-Mars injection maneuvers, and then Mars insertion maneuver, where you would actually operate the engine. At all other times, you would have coasting of your vehicle, sort of speaking. You don't operate, so you don't have to turn on the vehicle or the engine. And the last maneuver is the trans-Earth injection. Okay, so you have basically 4 maneuvers, and the system really operates for about 2 hours. That's it. Okay, so you don't have that concern of sort of depleting the fuel, because depleting the fuel is associated to how long you would be able to operate that. Okay, here the objective is to satisfy that very high temperature application. Okay, so it's completely different from a standard light water reactor application, where you want the fuel to spend in the core for about 1.5 years or 2 years. Here you want that to operate for 2 years, and you want to squeeze as much power as you can to get to those very high temperatures. Makes sense so far, right? Mm-hmm. And so, so what was your question?
It was just about how the design challenge of this really high heat is being approached.
Right. So here, what you want to do is you want to have a material that has a high loading of uranium, what we call the heavy metal loading, but you also want to use a material that has very good thermal properties, with high conductivity, for instance, would be one of them. Mm-hmm. Because you almost don't want to create, because as I said, the propellant temperature eventually would reach a temperature of 2700 Kelvin, which means that the fuel would be hotter. If the conductivity of the fuel is very low, then you can breach and violate your safety of your fuel. You can melt it, for instance. Mm-hmm. And so the industry, NASA is leading that, was leading that, and has multiple industry partners like BWXT Technology that are looking on manufacturing the fuel and testing this fuel in different facilities in United States. One of them would be the transient facility in Idaho National Lab. So they've already manufactured the fuel. They're in basically two main forms of fuel that they're investigating. One is a ceramic material. So those are, and again, there are probably multiple variations. I will just tell you what I know at this point. Those uranium nitride particles coated with zirconium carbide, put in a zirconium carbide matrix. This is what I call the ceramic. And you also have a refractory matrix, which is typically a tungsten matrix that hosts those particles. And those are really the options that are looking, investigating right now. Uranium nitride has this high uranium loading into the system, so you load a lot of that fissile material essentially, and that's the first benefit. And second of all, the thermal properties are also enhanced, where you compare them to a traditional uranium dioxide fuel, for instance. I do want to say that during the Rover and NERVA program, they were using highly enriched uranium fuel for their designs. And yes, we are borrowing a lot of the characteristics from the previous systems, but one of the main changes that was made was the choice of fuel. The choice of fuel now, with discussion of proliferation, but also with the economic benefits of manufacturing multiple engines eventually, led us to adopt the high assay low enriched uranium. In less complicated words, enrichment of below 20% rather than enrichment that was previously used of above 90%. Okay, and this leads to a major modification to the previous series of reactors, like PIWI, for instance. Now we have to change the design itself to accommodate for the fact that we load less fissile material, if it makes sense. And we still need to operate for those 2 or maybe slightly more hours for operation. Yes.
Awesome. And so looking into the future now, when do you see this technology coming to fruition, and how will it impact kind of the rest of the industry as a whole?
Oh, it's an excellent question. I don't build them myself, so I'm not entirely sure when. But so NASA was involved in this since I came to Georgia Tech, and I started doing this research with my undergraduate students, and after that with a lot of my graduate students. And I think that in Georgia Tech I had more than 20 students involved in this project in the last 6 years, which is very impressive in my opinion. Yeah. Undergraduate students and graduate students. Apparently, flying nuclear reactor makes students come to my lab.
That's awesome.
Yeah. So NASA had a big project to develop this technology and to revive the technology, I guess. And recently, there was an announcement made that NASA and DARPA, they joined forces to develop and deploy this technology, a prototype technology, by 2027. So coming back to my previous story, when those students came, I only looked at this as something that interested me from the research point of view. How would you analyze those systems? What would be the benefit of those systems? But now, I mean, it seems like there is a real chance that United States will build its first flying nuclear system by 2027. And that system, from what I understand, would not really be used for Mars application, but only be used as a flight demonstrated vehicle. Yeah.
Right. Okay. Well, I think those visions for the future are a great note to end on, unless you have anything more to add that we haven't covered yet.
I think we've covered a lot.
I agree, and that's awesome. Well, thank you so much for coming on. It was a pleasure to have you, and yeah, that's the end of that.
Thank you very much for hosting me.
And initiate at least a new approach to the many difficult problems that must be solved in both private and public conversation if the world is to shake off the inertia imposed by fear and is to make positive progress toward peace.